All right, 11:10. Let's get started. Any questions on anything we have done so far? All right, pipe down, please. Let's go to where we stopped. All right. Online students, can you all hear me? No, Zoom, yes. Okay. Electrical current, electrical voltage, electrical power. We can make a rough analogy with a mechanical system. Let's say we have a pipe which is conducting some fluid flow. There's a valve in there to actually block the flow or permit the flow as the need may be. Similarly, we have a electrical conductor, which is basically a piece of wire that allows the current to flow through. We need a closed electrical pathway for the current to flow through. It cannot be open. If it's open, we call it an open circuit. If it's closed, we call it a closed circuit or closed loop. Most common example of a open circuit is your AC power outlet. It's open, right? Current does not flow through until you plug something in there. When you plug something in there, whether it's 2 prongs or 3 prongs, let's stick with 2 for now. Current enters through one end, goes into your device, flows back into the wall outlet through the other prong. If you take a piece of wire and you stick it into those 2 openings in the wall, what do you think happens? No one's ever tried that? It'd be a small spark, small explosion, right? Dangerous. You do not want to do that. The reason is you take a piece of wire, it has very low resistance, you stick it into the 2 openings, you now have a closed loop. Current can now flow through, but the voltage is so high, the current is so high that the wire cannot handle the amount of heat that is generated and it blows up. If you have a very thick piece of wire or a component that has high enough resistance that it can impede or slow down the flow of electrons, then yes, you would not see anything except the component might heat up. That's it. But again, the point being, it needs a closed path for it to flow through. That's also, by the way, that is also the operating principle of an electrical fuse. An electrical fuse has a small piece of wire inside it. It has a certain power rating. If the power rating or the current flowing through that wire exceeds the rating, it cannot handle it and it just blows out. When you say fuse blows out, that is what is happening. It's actually breaking it. And when it breaks, the circuit is now open. There is no pathway for the current to flow through. So it's used for circuit protection, right? So a mechanical pipe can be said, or not said, can be analogous to an electrical conductor. The flow of electrons would result in the flow of current. And so we could equal that to a fluid that is flowing through the pipe. Okay, conductor, fluid flow. Okay, mechanical valve as analogous to an electrical switch. Mechanical valve, again, this is just a very crude illustration. Electrical switch is noted like this. And we will study, or not study, but we will actually use this symbol in chapters 3 and 4. More in 4. So you may be used to the term in a closed valve or open valve, right? For an electrical switch, it is exact opposite. Right now, is this switch open or closed? Okay, right? It's intuitive. You may have seen this before, but now you know what an open switch looks like. So this is an open switch. If a valve is open, it will permit the fluid flow. But if a switch is open, it will block fluid flow. Conversely, a closed valve will block the flow but a closed switch is required in order the current to flow through. Okay, closed switch is required in order for current to flow through. Right? Make sense? So then let's take a look at what we need to do when we begin circuit analysis. Now, the beginning of a problem, we would be given certain values. We might be given, okay, the source has a certain voltage, source has a certain current. The values of the components will be given to us. But other than that, we might have no idea of the voltages and the currents that are appearing in the circuit. So when we first begin analysis, we simply assign values randomly. Those values are completely arbitrary. We make certain assumptions before we begin our analysis, but those assumptions are based on certain logic. Okay, those assumptions are based on certain logic, but they are completely random, completely arbitrary. Okay, so in this case, we are given I1, I2, I3, we are given the voltage polarities. They're completely random. You make assumptions, but those assumptions are based in logic. Okay, it doesn't matter what assumptions you make, but once you make an assumption at the beginning of your problem, you stick with your assumptions for the entirety of the problem, right till the end. And if your methods and techniques are correct and you didn't make any errors, you will end up with the right answer. You do not change your assumptions halfway through your problem. Then you will arrive at a wrong or incorrect answer. Yes. Actually, no. When I say values, I'm talking about the directions and the polarities. Should probably change this. Direction of current and voltage polarity. The point remains, you choose and assign current direction and voltage polarity at random. You make an assumption. The assumption is based on logic because if we know the positive and the negative end of a component or of an element, then we know current flows from high to low. It goes from plus to minus. We'll just see that in a couple of slides. Okay. All right, current direction. We use two subscript notations to note current and voltages, and for two terminal elements. Now, all of the elements that we see in this class, resistors, capacitors, and inductors, they all have two terminals. So we refer to them as two terminal elements. So all two terminal elements have two ends. In this case, it is A and B, right? It shows that this is a resistor, but it could be any element. Does not really matter. You establish the voltage polarity, you establish the current direction. Whether it's given to you or whether you're making an assumption does not matter. But once you have the voltage polarity and once you have the current direction, you can begin your analysis. Okay. The two subscript notation is used to note a current going from point A to point B or vice versa. So if I choose IAB, I'm referring to the current that is going from point A to point B. The first subscript is always the point of origin or the point of entry. So IAB points the current going from point A to point B. IBA is referring to the current going from B to A. They are one and the same thing. So I can simply write mathematically IAB is equal to minus IBA, or IBA is minus IAB. Okay. Again, the minus sign is just for us to balance out equations. Otherwise, the equations would never balance out. Okay. Similarly, one additional point. If this resistor or this element is called as, let's say, R1, that's just the name of the resistor that we assign, right? Or it might be assigned to us in the circuit. Then if I write IR1, you again have two subscripts on there, but IR1 simply refers to the current that is flowing through element R1. That's it. It's not noting anything else. It's not noting the terminals. It's not noting anything. It simply refers to it as saying current I flowing through resistor R1. Yes. What? IR1, IR2? It could be anything. It could be anything. It just depends on what direction current assume at the beginning of the problem. And then if your answer ends up to be negative, it still is correct. As long as the numerical value of your answer is correct, then the plus or minus sign is taken along with the current direction or the voltage polarity. Okay. So it does not mean that your answer is incorrect. If you make an assumption at the beginning of the problem saying that the current is flowing from A to B, and then IAB ends up being negative, let's say minus 5 amps, for instance, then I would look at the current direction that you marked on the circuit diagram, and I would look at the minus sign, and I would say, okay, yeah, that is correct. So it doesn't really matter what you get at the end. As long as the current direction matches up with the answer, you will get full credit. Same thing with the voltages. The voltages have polarity, and so we have two ends. We have a plus and a minus. If it's an element R1, we would simply say VR1, meaning voltage for the resistor R1. But if you're talking about the two ends of the terminal, A and B, then we would say VAB refers to the voltage that is being measured at A with reference to B. Okay. Voltage measured at A with my reference at B. So B is minus, A is plus. Conversely, VBA simply means voltage being measured at B with my reference at A. The reference comes into the picture because voltage is again defined as the difference in electric potential between any 2 points. For there to be a difference, you need a point of reference. VAB could be like, I'm standing at B, which is my reference point, and I'm looking at A. I'm measuring the distance between A and B. Okay. So VAB simply means I'm measuring the voltage at A with my reference being at B. And as with the current direction, I could write VAB is simply minus VBA, or VBA is minus VAB. Let's take a 10-second pause. Think over it. Let me know if you have any questions. Yes. Well, just for that particular measurement. The actual value could turn out to be negative. Doesn't really matter. Like B could be at a lower potential than A, or A could be at a higher potential than B. But in this case, VAB simply means you're measuring voltage at A with your reference at B. If you actually had a multimeter, the multimeter has plus and minus terminals, which if you're taking 251 or any lab you might take, if you look at a measurement device, it'll have plus and minus terminals. If you're measuring VAB, what you would do is you would take the negative terminal and you would put it on the second subscript, because that is your point of reference. And then you would take the positive terminal and put it at the first subscript, which is A. Okay, so that plus minus has nothing to do with the actual voltage measurement. It could turn out that VAB is minus 5 volts. All it means is that you're measuring VAB, you would simply switch it out to VBA and you would get plus 5 volts. Make sense? See some confused faces. All right, any questions? Yes. Yes, but it depends on the problem. As long as you have the right numerical value along with the marked polarity of the voltage, you'd still get full credit. Are you asking in terms of analysis, theoretical analysis, or actual physical measurement? It doesn't matter. You could choose. So right now, not in this example, but if you go to the previous example where we assign voltages randomly, right? So let's say V4. V4 has a minus on the left and a plus on the right. You'd perform your analysis, you'd apply like KCL, KVL, whatever techniques we want to, and we arrive at an answer of V4 is equal to minus 5 volts. Some other student might choose this polarity. Now, of course, whatever you choose should be marked in the circuit diagram. We call this as the circuit schematic or the circuit diagram. So if another student chooses the polarity as plus on the left and minus on the right, they might arrive at plus 5 volts. Now, did I say 5 or 4 earlier? Doesn't really matter. Let's say the answer is 5 volts, right? One student chooses the polarity here, student 1. Another student chooses this polarity right there, number 2. So if this answer turns out to be, let's say, minus 5 volts, and this answer turns out to be 5 volts, they are both correct. Does everyone see the point I'm trying to make? They are both correct. As long as your plus or minus sign matches up with what you assumed in the circuit diagram, you will both get full credit. You do not have to explain that, oh, my polarity is opposite. And no, it doesn't, I understand. I understand. Yes. Reference is the point from which we are comparing the other point to. So you remember last class where I had this kind of diagram? Because voltage is the difference in potential between 2 points, meaning there has to be a point of reference. We are comparing the electric potential at 2 different points. So the second point is always the point of reference in the 2 subscript notation. That is our, you could say that is the starting point, if that makes sense. Okay, my starting point could be anything. Starting point could be 0, 1, 2, doesn't really matter. But that is always the point of reference. That's my baseline. All right, we were here, voltage polarity right here. This right here, positive reference at the head of the arrow, is not used a lot. I've rarely ever seen any circuit diagram by any author which would actually use a reference direction that is portrayed like this. Typically, we would have something like this. You'd have an element. That element simply has a plus and a minus at either end. If some books or some papers or some authors use an arrow, it's usually like 2 arrows. So you'd have a plus and a minus here. And you simply say this is voltage Vx, positive is there, negative is there. You'd have two-headed arrows in both directions. You would not simply have one. If you have one arrow without a plus or a minus sign, it indicates plus is here and minus is here. This is just for like general knowledge for you in case you ever see a circuit schematic with something like this. But again, in all my years in E, I want to say almost never seen anything like this. Mostly it's just plus minus clearly noted on the circuit diagram. All right. Okay, Ohm's law. Ohm's law is something, this is one of the most fundamental equations of electrical engineering. You can solve pretty much any circuit with it, or actually most of the principles and most of the equations and methods use Ohm's law. There are many memes, but I like this one. It just shows the voltage, the relationship between the voltage, the current, and also the heat that is dissipated when current flows through a circuit. Okay. I assume students are familiar with this from physics 3, probably even high school. But again, we definitely do a recap, a brief recap of what it is. So George Ohm, again, physicist who did some research in this equation that he came up with, simply states that the voltage in an electrical resistor is the product of the resistor and the current that is flowing through it. V equals IR. V equals I times R. You can solve pretty much any circuit with this. Or conversely, it would be impossible to solve any circuit without this equation. Volts equal to amps times ohms. Okay. Voltage is, of course, the difference in potential between 2 points. You could make an analogy with a pressure differential. So there's a difference in pressure at 2 ends, like a pump. Then you can push electrons through and result in current flow. Okay. From this, we can rearrange the equation and come up with I equals V over R, or R is V over I. You do not have to memorize everything. If you can, that's great. If not, you simply use Ohm's law and then work from there. All right. Energy and power. Okay. Sources always supply power. They always supply energy. Loads, resistor, inductor, capacitor are all loads. They cannot supply anything of their own. They always receive power. They always receive energy, right? Law of conservation of energy always applies in a circuit, in an electrical circuit. If a source is supplying electrical energy, then that total energy being supplied always has to equal the rest of the circuit that is receiving that energy. Okay. Whenever a source is supplying energy, you apply voltage, you send current through the circuit, right? Energy is being transferred. When energy is being transferred, some of it is absorbed and some of it is lost as heat. You just saw that meme, right? You sure do get hot doing my work. So you supply energy to a resistor. Resistor will oppose the flow of electrons. It'll dissipate a lot of that energy as heat. So they get hot. Electronic components, even solid state devices, tiny microchips. There is exchange of energy. When there's an exchange of energy, they dissipate energy or they lose energy as heat. That energy is on the order of nanowatts and picowatts, even femtowatts, very, very small, 10 raised to minus 9, minus 12, minus 15. But if you have a billion transistors on one circuit, which is 10 raised to 6, 10 raised to 9, and we are even pushing those limits, more and more transistors on one circuit, right? Billion is 10 raised to 9. So even if each of them was releasing just like 1 nanowatt or even less, you combine all of those together, billions and trillions of transistors, you're now talking about tens of watts. And that is the reason why your laptop gets hot, because it has billions of transistors. A lot of the energy is being dissipated as heat. And so all billions of them working together, that energy is all combined and, well, is lost as heat. So when we want to balance out our equations, again, we have to keep the law of conservation of energy in mind. Everything has to sum up to zero. A real life physical adapter, a physical power source, is only rated as, let's say, 500 watts, 200 watts. We don't say it is rated for minus 200 watts, right? But mathematically speaking, if you want to balance out equations, we put a minus sign in front of that source. And so that's the logic behind this slide. How do we know where to put a minus sign and where to put a plus sign? Well, the information about voltage polarity and the current direction is given to us, or we make an assumption. That assumption gives us plus and minus for the voltage polarity, which is right here. And then the direction of the current. If the current enters the negative end of that element, we say that the energy is being supplied or power is being supplied. If the current enters the positive end of that element, we say that the energy is being received or the power is being received. Think of this as money. If you lend $100 to your buddy, most likely you'll never see it again. So now you supplied money, you supplied $100, your account has a net negative balance. Or basically it was a negative on your balance sheet. On the other hand, if you found $100, it's a positive, right? You're receiving. And so if the current enters the negative terminal, power is negative, energy is being supplied. If the current enters the positive terminal, power is positive, energy is being absorbed. The rate of energy transfer is the power equation. It simply is P equals VI. Power is the product of the voltage and the current. If power is negative, we simply use P equals minus VI. So on this side is minus VI. On this side, it's plus VI. Does that make sense? Positive and negative power. If we combine this power equation with Ohm's law, we get two more equations. We're simply rearranging the terms. We plug in Ohm's law into the power equation, and we can get P equals I square R, or P equals V square over R. You do not have to memorize these two equations. Okay, you can always derive them from Ohm's law and the power equation. So again, I do not expect students to memorize it. If you can apply directly, great. If not, do not worry about it. As long as you have the two equations, it's fine. And you can always have them on an equation sheet if you wish. But does it make sense? Any questions? Passive reference configuration, simply an extension of just what we talked about. A, B, C, and D. Let's look at A. Where is the current entering? Positive or negative terminal? Positive, so power is positive. So P equals VI. Look at D. If you look at D, current is entering the negative terminal, so power is minus VI. If you look at C and B, we extend the current right here. And for B, I can see that the power, the current is entering the positive terminal. Power is positive. We use the equation P equals VI. For C, current enters the negative terminal, so power is negative. We use the equation minus VI. And that's it. As easy as that. If current enters the positive terminal, power is positive. If current enters the negative terminal, power is negative. You do not worry about what the end answer would be. And in the next slide, we have an example. I will show you specifically what I mean. Yes. Yes. So on the right side, it's entering the negative terminal. So power is negative. So it's P is equal to minus VI for D. Same thing for C. If we extend the arrow for I, again, because it's the same electrical loop, we see that the current is entering the negative terminal. So power is negative. It's minus VI. Again, when I say power is negative, I just mean mathematically, okay? Not real life. In real life, power is just power. We don't say this adapter is rated for minus 500 watts. Just mathematically speaking. Let's look at some examples that will make it clear. So again, the assumptions at the beginning of the problem are already made. We have the values, we have the current directions, we have the voltage polarities. Whether they are given to us or whether we make an assumption is irrelevant at this point. We simply look at the information that we have and we choose which equation to use. So for A, current is entering the positive terminal. So power is positive. I use the equation P equals VI. I plug in the values. Therefore, P equals 12 times 2. Final value for P is 24 watts. Oh, by the way, when you're solving and showing your work in quizzes and homework and the final exams, these are the steps I want to see. The first step is you would set up the problem, meaning you would mark all the currents, all the voltages in the circuit diagram, in the schematic. Then you would write down the equations, enter the values, and then you have the final answer. Do not skip steps, okay? I do not want to see P equals VI and then there's a final answer. There is a purpose to that. As engineers, you are supposed to be detail oriented, so you don't end up making errors and mistakes. One of the ways to reduce errors in your work is to proceed step by step. Okay, so do not skip steps. Units are very important. 24 watts is the same as 24,000 milliwatts or 24 million microwatts. All answers are acceptable. But the whole point of using unit prefixes is because we don't have to write a large number. So 24 watts, again, is the same as 24,000 milliwatts. Answer, both are correct. So do not forget units, do not forget unit prefixes. Yes. Where? Oh, here, because we are referencing the name of that element. Good question. The question being asked is why is there only one subscript? VA is simply referring to the voltage for the element A, and the plus and minus sign is always already given to us. So we don't really care about the second subscript. But if the terminals were noted, then yes, we would say VAB or VXY or something like that. Yes. Yes. Yes, exactly. Yep. But these examples are for determining which equation to use. And so we already have the polarity and the direction. All right, second one. We extend the current entering the negative terminal. The equation to use is minus VI. So power is negative, we use minus VI. Minus 12 times 1. Minus 12 watts. Again, we don't really care that the answer is negative. But the answer is negative simply means the element is supplying power. It's supplying energy. Okay. How about the third one? Power is negative or positive? Some hesitancy. Don't look at the numbers. Simply look, again, as I said, go step by step. The first step to do is to determine the current direction and the voltage polarity. In this case, we already have both. Polarity is given to us, direction is given to us. We simply see that the current is entering the positive direction. So it's a positive power equation. We use P equals VI. Next step, enter the values. P equals 12 times minus 3. Simply solve it. Do not get too worried about the negative sign. Your final answer is minus 36 watts. At this point, we don't care about the voltage polarity. We don't care about the current direction. Our answer is negative. It's a positive power equation, P equals VI, but the final answer is negative. That means that the energy, that means that the element C is supplying power. It is supplying energy. That's all it means. And that was the specific example I was talking about. You go step by step. You make a certain assumption at the beginning of the problem. Then from that assumption, you write down the equation. In this case, at the beginning of the equation, it was positive. Then we plug in the values. The final answer is negative. It does not mean that your assumptions were incorrect. Okay. In this example, the direction was already given to us. But at the beginning of your problem, let's say this was an assumption you made. Along with the direction and the minus sign, your answer is still correct. You still get full credit. I keep emphasizing this because students I've seen over the years, over and over again, there'll be some students who do get bogged down. They will see -3, then they will flip the direction of the current, and then they, instead of using P equals 1, VI, they would use something else, or they might see first, okay, it's plus, so I use P equals VI. But then because it's given minus, I need to change the direction of the current. And instead of doing 12 times -3, they would do 12 times 3 and end up with the incorrect answer. So again, that's why I keep harping on that, right? Make an assumption and stay consistent till the end of your problem. You will end up with the right answer and full credit. Okay. All right. Oh, any questions about the previous slide before I moved on?
I have a question, Professor.
Yes, go ahead.
How do we think of current in this class? And what I mean by that is in physics 3, we think of a positron leaving the positive terminal
Yes.
to the negative terminal. Is that how we think of it in this class as well?
Yeah, so it's a good question. We're talking about physics, right? So current is the rate of flow of charge. Charge is carried by electrons. Electrons can move within a physical space, right? Protons are bound. So when an electron moves out of a space, it leaves behind a hole. And literally, it is known as a hole. The technical term that we use in semiconductor physics is a hole. A hole has a positive charge. An electron has a negative charge. So what the question being asked is about, are we talking about electron flow for the current, or are we talking about hole flow for the current? We are talking about neither. So do not get bogged down into the physics of things. Again, we can go into semiconductor physics, and I could talk about that all day long. But the answer is we won't reference the flow of electrons. We won't reference the flow of negative charges or positive charges. We'll simply reference the flow of electric current. With regards to the plus and minus sign, I would say that for all elements, passive elements, the current always goes from high to low. So it always goes from plus to minus. So remember when I said we make an assumption about an element? So let's say we had a circuit and we assume that the element had a plus and minus sign across its two terminals. So let me give you an example right here. Let's say we have this element and we have no idea of the voltage or the current direction. Element X. We assume that element X has a plus on the left and a minus on the side, minus on the right. Okay, this is an assumption that I am making in order to solve this problem. Then logically, remember I said the assumptions are made in certain logic. Once I assume a voltage polarity, if I know that the element is not a source, the current goes from plus to minus. Do not worry about electron charges or hole charges. Positive charges, negative charges, we're not worrying about charges at all. Again, we are not going into physics. We are not going into semiconductor device physics. We are simply looking at electrical current, not at electrical charges. If it's a source is supplying energy. So the current flow for a source goes from minus to plus. Again, that will come in later examples. But since the question was being asked, I'll point it out right now. Current for all passive elements, basically resistors, capacitors, and inductors, always goes from plus to minus. Current for a source will always go from minus to plus. Does that answer your question?
Yes, it does. Thank you.
Okay. All right, moving on. I don't know why I increased my volume. I just felt that somebody's online, so I was talking louder than normal. Anyway, how do you say this name? Right, Kirchhoff. So when I first heard Kirchhoff in a department meeting, I was like, who are they talking about, and why do I not know this? I was like, somebody help me out here, you know. But I'm from India. The way we say this name is Kirchhoff. The actual German pronunciation for this name is Kirchhoff. Kirchhoff. Now, obviously, you know, this name probably is in existence today. Somebody out there is probably named, you know, has the same name. But none of us lived during his time. He was a German physicist and a scientist who did research in electrical currents and voltages and came up with 2 laws pertaining to currents and voltages in a circuit. And they are known as Kirchhoff's current law, Kirchhoff's voltage law. So anytime you hear me say the word Kirchhoff, this is who I'm referring to. For the most part, we just use acronyms KCL and KVL. Okay. And they are both brilliant and elegant in terms of the simplicity. Simply states that the current entering, all the currents entering a junction in a circuit always sum up to 0. And all the voltages around an electrical loop will always sum up to 0. So you may have looked at these laws in physics previously, and you may have your own preferred technique. I'm not here to force my techniques on you. If you have a preferred technique to deriving this equation, absolutely fine. Go ahead and stick with it. But the way I use and apply KCL is this. I simply write out my equations. Let's say we have a junction. And I have IA and IB entering and IC and ID leaving the junction. I'll simply have an equation or equal to sign. All the currents that are entering the junction, I put on the left-hand side of the equation, and all the currents that are leaving the junction, I put on the right-hand side of the equation. And so I get IA plus IB is equal to IC plus ID. As easy as that. Is this the way that you have learned it? Or at least most of you have learned it. You can assign direction to the current, but then it just gets confusing. Like you could say all currents entering are positive, all currents leaving are negative, and you could sum it all up. So you could say IA plus IB minus IC minus ID equals 0. Same equation, doesn't change, right? Same equation. IA plus IB minus IC minus ID equals 0. Or you could say all currents entering are negative and all currents leaving are positive, and then do minus IA minus IB plus IC plus ID is equal to 0. I just think this is the most common and the most easiest way to implement it. All right. Think of it as a traffic junction. All vehicles entering a junction have to equal all vehicles leaving a junction. Otherwise, you'd have diehard 4. Anyone remember that scene? If you've not seen that movie, the first 4 movies, by the way, excellent. 5th one was okay, not so much. But there's a scene in the movie where hackers get into the traffic system and turn all lights at a junction into green. All vehicles converging in a junction all at the same time, right? Which is not accidents. In an electrical circuit, that's not possible at all. There's a physical basis in real life for current to flow through in a circuit. You can never ever have 2 or more currents all converging at the same time into a junction. It's just mathematical equations that assign directions as well as plus and a minus sign. Okay, so let's look at this example right here. Let's look at the left, A and E. What do you see? They're in series and they are the exact same current, right? They're the exact same. There is no break between A and E. They're exactly the same. Think of it as a street. Okay, think of it as a street. If it's a one-way street, there is no other direction for it to flow. It's just flowing in one direction. But the direction shown to us is exactly opposite. IA and IE are going in the opposite direction. Again, this is just for mathematical purposes, for analytical or theoretical purposes. There is no basis for this in, there is no physical basis for it to have opposite currents. I can simply write IE is equal to minus IA, or I can write IA is minus IE. Both of them are correct. So I can simply write IE is minus 6 amps. Easy enough. How about on the right? C and D are exactly the same example. Again, C is given to us as minus 2. I can write ID is minus IC. So it's minus or minus 2 amps. The only thing remains is applying KCL here above at 1 and at 2. If I apply KCL at 1, I see that there are 2 currents entering and 1 current leaving. So the 2 currents entering are IA and IC, which equals IB. IA is given as 6. IC is minus 2. Therefore, IB is 4. Again, 3 currents entering at junction 1. 3 currents at junction 1. 2 of them are entering. IA and IC are entering, and IB is leaving. I write out my equation, plug in the values, and solve. If I apply KCL at junction 2, what do you see at junction 2? Die hard 4 again. You have IE entering, IB entering, and ID also entering. They all sum up to 0. Let me scroll right there. So again, junction 2 is right here. You have IE, IB, and ID all entering the junction. Doesn't have to make physical sense, but it does make sense mathematically or analytically or theoretically, if you will. You plug in the values. IE is minus 6. IB is 4. ID is 2. Do they sum up to 0? Yes, KCL is verified. That's it. Okay, any questions? Now the homework assignments on Pearson, I had to set some dates, otherwise they wouldn't have been available to students. So I set it for Friday, Saturday, Sunday, Monday. Okay, but only homework 1 will be due today. The rest, I will, extend it by like a day or 2. So unless and until the material is covered in class, do not assume, I would not assign it to the students. Conversely, in my homework on the syllabus, it states once the material is covered in class, consider it to be assigned. Okay. All right. So we'll end class here today, and I will see you all on Tuesday. If you show up on Monday, it's going to be an empty campus because it's MLK Day. So I have a good weekend, and I will see you all on Tuesday. All right.